For the past 3 years, my company Cool Street has been working on solving charging for EVs for people who park on the street. And today I want to take you back in time and show you our very first prototype. And this will probably be more interesting for you engineering types, but hopefully it's not terribly boring for everybody else. Let's start with the problem again. I'm not going to belabor it a lot, I talk about it a lot, but the problem for people who park on the street is that filling up an EV with electricity is fundamentally different than filling up a gas car with gasoline. You're putting equivalent-ish amounts of energy into them. However, the gasoline can just be pumped in a couple minutes, and electrons, they don't really do too well getting shoved into a battery real fast. That is getting better. Batteries can take more, but there's another issue that people don't generally talk about when it comes to filling up an EV fast, and that has to do more with the grid capacity and the capacity for that charger. If you could fill up an EV like mine, my Chevy Bolt, in about 4 minutes, so make it roughly equivalent to gasoline-powered car, the amount of power flowing into my car over that period of time is equivalent to the average-ish daily consumption of about 750 homes, which is a lot of power. And if you figure that's just one car filling up, you can start to see the problem of having the capacity to pump that much juice into a vehicle. However, the advantage of electric vehicles is that these things can fill up really well at slow rates. And if you plug this in at night and fill up overnight, you're only really consuming, say, a high-powered dryer load, a little bit more than that. You can even turn it back in a lot of cases because you don't need to charge that fast. So it's really manageable if you bring that charge rate down, and that's gonna have to persist into the future. I don't think everybody can charge at a fast rate, even if the batteries can accept it. For people who park on the street, this boils down to you need to have charging where you park overnight, or you need to have some other solution, like if you go to work and you can charge there. But ultimately, you're gonna have to have something where people park overnight because not everybody goes to work, especially post-COVID. And there's all sorts of situations with retirees and all these weird edge cases where the workplace charging isn't that viable. This was the foundation of why we created Cool Street. We saw there's gonna be a huge issue here, and if people cannot get charging where they park overnight, they literally really can't go electric. So back in 2021, I started looking around at what options were out there for charging on the street, and there really wasn't much, at least in North America. There was some things by Flow, and maybe ChargePoint had some commercial units that you could put on the curb, and some cities were starting to do that, but they were limited to like really big cities, New York, LA, places like that, where they could afford to put that investment in without much expected return. In a little city like mine, my city's not going to trench up the right of way in front of my house and put in a charger just for me. In fact, I might just move, and then who's going to use it? None of my neighbors have EVs. The revenue off that is extremely low. More cities have come on board in the past couple of years with this, but it's still really, really rare to find curbside charging of any sort in the United States, especially in a really low parking density, almost quasi-suburban setting. There's also the size issue. So all of these commercial and big solutions that are out there installed by the cities, they're huge. I mean, these things are 10, 12 feet tall and huge eyesore. I wouldn't like that. My neighbors who drive ICE vehicles especially wouldn't like that. And so this was just a no starter off the gate. I realized I had to take this into my own hands. Nobody else was gonna do it for me. And there was a couple things that I needed to address. One was make it super discreet so that I like it, my neighbors are okay with it. Two, power this off of my own power supply. That way I can get it out there relatively cheaply. The city doesn't have to worry about running power. That gets them off the hook, and everybody is happy. Now, along with that, we do need to make this publicly addressable. It's in a public location. So to get that okayed by the city, it's going to have to be something that can be used by others. And so to do that, we will build out a network that other people can use to charge, and basically we're sharing chargers among ourselves. My first idea was to hide the thing underground. And so the idea was you have a charger in the house, you put this retractable cord reel underground, kind of like an air hose winder-upper thing, and you retract your cord down into this underground vault, and you lift up a cover when you need it, you pull out your cord, plug it in your car, it retracts back into the ground when you're done. It's kind of a cool idea, and I worked on it a bit, but ultimately it was complicated, it was very expensive, and probably more importantly, water likes the ground, and flooding, it would fill the hole, and so electricity and water don't mix, and obviously you can see bad things would happen there. Now, I wasn't totally blind to things that were happening around the world, and I was looking quite a bit at Europe because they're ahead of us on this. They have a lot more street parking, a lot more people without access to charging at home. And so they've come up with all sorts of different solutions. There's a charger that pops up out of the ground and you can plug a cord into it, and then when you're done, it retracts back down into the ground. There's another one that's flush mounted, and there's this lance that plugs into the jack on the ground, and when you're done, you just unplug it, throw it in the trunk of your car, and go. And then there's other ones that are just simple bollards with outlets on them. And I looked at those and I said, hey, I like this. It doesn't have the complexity of a telescoping retractable thing that has to go into the ground. It's much more simple, just having a simple post and socket. You know, you don't have to worry about things like icing so much. It can be protected from the elements better, like rain. And ultimately, it's more reliable and just a pretty clean way of doing it. Yes, it doesn't go flush, but if you paint it a dark color or something that hides well in the environment, this thing is super discreet. So the next question was, what do we use for a cable? In Europe, they use the Mennekes Type 2 connector, and this is a connector that can handle three-phase power because a lot of their homes have three-phase electricity. Now, in North America, virtually none of our EVs can even accept three-phase electricity, and neither do our cord standards. So our cord standards are J1772 and the Tesla NACS connector, and both of those are single split-phase connectors. So it didn't make sense for us to bring over the three-phase connector, and this is a few years back. There wasn't really anything in the US at the time standardized, so I said, let's pull in the J1772 standard and see if we can make a socket with that. I had a cable, I had a post, and I had an idea, but the problem was I'd never built a EVSE or an AC charger before. And so I looked around at what was out there. I was fully prepared to take this on myself, but I wanted to see if there was anything open source that I could use and integrate into at least my initial prototype. And what I found was this really cool project that was started in 2011 called OpenEVSE. So OpenEVSE was started by some people who were just looking to see if they could charge I think it was a Nissan Leaf at the time, off of a very simple microcontroller. And they were successful in doing that. And over the years, they've built out this whole ecosystem. You can buy fully assembled chargers from them. You can buy all the individual components and build your own. And a lot of companies have actually taken these components over the years and assembled them as OEM products into their final product chargers. The foundation of the OpenEVS system is this little control board. It's super tiny, but this guy is handling all the communication between the charger interface, which is this board, and the car. And the primary function of this is to handle safety features, things like GFCI protection or making sure that the relay isn't stuck. But a big part of that is generating the 1 kilohertz square wave. The square wave runs down the pilot line to the car and tells the car how much power it can safely pull on the circuit that the EVSE is installed on. And when the car gets that signal, it says, okay, I will adjust the current I pull accordingly, and then it pulls the voltage down on that signal. This guy senses that drop in the voltage, and then it closes the relay to release power to the vehicle. So that's the controller. OpenEVSE has created this controller. They've created the firmware for it. It's all open source, so you can go out and modify it to your heart's content. And I got my hands on one of these. I said, I want to use this. It's nice and small. I can fit it inside of a post or a small structure, and it has many more capabilities. One thing OpenEVSE can do is to measure the current going to the vehicle, and they sell these coils that can go around one of the legs going to the vehicle, and it will sense the current going to the car. They also have the GFCI coil, so this is a safety feature. You put this around both legs, and this will detect ground fault current leakages. That one's pretty much required. They also sell things like a text LCD screen so you can display information. They have temperature sensors and lights. And most importantly for me, they have a Wi-Fi board. So this will turn the OpenEVSE controller into a smart charger that has a web GUI that's stored on your local network. And so that allows the user to really look at everything that's going on the charger and adjust a lot of settings. It has a lot of integrations into third-party apps and things like that too. So this thing is quite powerful, and over the years they keep adding features to it. For my first prototype, I ordered up the controller, the Wi-Fi board, the GFCI coil, and the power coil. And then I had to decide on what do I put it in. I decided on a simple 4x4 steel post, and I had a local machine shop kind of put the thing together for me, including a cutout for my socket. So the socket was the fun bit. I spent a lot of time on this socket. You can see it's a J1772 connector. It's sloped downward. The reason for that was basically I could have water shedding off of the socket without having to have a door. I was looking to maximize simplicity at this point. I didn't want to have extra parts if I didn't need them. Enhances reliability, lowers the cost, etc. Now, the pins on this guy are also sealed individually, so even if you do spray water up into there, it really shouldn't leak into the inside. And the other thing about this is when you plug your cord in, it's angled down nicely so that it's not sticking straight out from the post. So on the back of the socket, I created a spot for the contactor and the coils. The controller and the Wi-Fi board are located inside the cap, and they were just kind of open inside there, and then there was wires between that and the things in the socket that it controlled. So to wire this up, you run the 2 phases of your split phase 240 service into the bottom of the post through a conduit. You also run a ground wire with that. And the 2 phases, or the 2 legs, attach to the contactor. And then they flow through the contactor to the power pins on the J1772 socket. The ground comes up as well. This ties into the electronics ground, and then it also is tied into the post shell. And that's super important because if something fails in here and one of the hot wires rests against the post, we do not want to electrify the post. That would not be good if somebody touched it. So that was a really important safety feature. Ground out the post, just like any old conduit that you would do or electric box. In addition to grounding out the post, I also implemented a way to disengage power on the socket before you pulled out the cable on the EVSE side. That was an important feature. You don't want to disconnect hot. It also has GFCI, so it is protected against ground fault shocking. So if somebody would inadvertently touch it, it would behave very much like the outlets in your bathroom or your basement or somewhere, in a wet location like that. So I did implement as many safety features as I could into this, even though it was just a prototype, because yeah, I didn't want anyone getting hurt. And that's how I got this thing all wired, up and running, and I tested it out in my garage for a few weeks before I deployed it as my everyday charger. And I was shocked at how good it was. I used this as my everyday charger for about half a year until it died, but until then it worked really, really well. I would just plug in, the thing would work, I'd unplug, it would stop. It was super reliable, super robust through the winter, through the snow, through the rain, through the cold, and it did fail. Although water and rain couldn't directly get into this thing, condensation could still form on the boards inside. And so over time, what ended up happening is they got wet, it messed them up, they stopped working, and this thing was out of commission. So the good thing that came out of that is it told me something that needed to be improved for the Mark II prototype, but that's a story for another time.